The idea with a composition is that you can take a function and you can combine two different functions to make a new function, right? A function is a relationship, and it turns out you can add or subtract those relationships. So, for example, if f of x is x squared plus 1 and g of x is 2x plus 3, these are relationships, but I can add these together to create a new relationship. So I can call that new relationship f plus g. This is the notation, the kind of the way we write that, because it's a whole new relationship, but it's based off of these previous two relationships. And with addition and subtraction or multiplication and division, there's no magic there. It's just, you just add the two together, right? If you're adding the two functions, you add the two formulas, the two outputs together, and you get, some new formula, but it's just the sum of those other two values. Okay. The same thing works with multiplication and division and subtraction. So it's kind of like we're already good with those operations, and so applying them to a function typically doesn't feel like a lot of extra work in some way, or some new idea. But compositions are a new way of putting two functions together. It's something that doesn't have a similar relationship with numbers. And the symbol we use for composition is this little circle, right? So f composed with g, or f circle g, but it really, composed is the right way to read that, like f multiplied by g, right? But this is not multiplication. This is something different. We already have another symbol for multiplication, right? The little dot, or the x. This is an open circle. So the question is, what does that mean? How do we put the two functions together? And what it means is we do them in a nested order. So f circle g, or f composed with g, is really just f of g of x. And there's never a situation where this is more useful than this. It's always better to write it as f of g of x. So if I ever see f circle g, I immediately write it or think of it as just f of g of x. And what that does is different than multiplication. G of x is 2x plus 3. I don't multiply that by x squared plus 1. This is my new input to x squared plus 1. So the function, again, it's like those little nesting dolls, right? Where you have like a small one inside like a bigger one, right? And so normally the small one is the x, right? The x goes into the function, but here we have this different thing, this 2x plus 3. So when that goes into my function f, instead of x, I have 2x plus 3 squared plus 1. It's the same relationship here, just with a new input. Okay, and so this is a new formula, just like before, but it's created from composing, or sort of linking, the two functions together. So the input x goes into g, and then whatever g does to it, that new value goes into f. So we could figure out the formula here by squaring this out. It's 4x squared. If you just FOIL it out, you're going to get 12x plus 9 plus 1. 4x squared plus 12x plus 10. So sometimes the questions will ask you for the formula, in which case they're looking for this value. But sometimes they might just say, what's f equal g of 2? Well, again, I would right away write that as f of g of 2. And I know the formula, it's right here. So one option, if you've already done the formula, well, then I should just put 2 into this formula, because that's what f of g is. And that's going to be 4 times 2 squared plus 12 times 2 plus 10, 16 plus 24 plus 10 equals 50. Now, if I hadn't already gone through this work to do the formula, it turns out it's just as easy to take the 2 and go through the steps, right? And the steps say I start with g of 2. G of 2 is going to be 2 times 2, which is 4, plus 3, that's 7. Right? And this is a good illustration of how compositions work. 2 is what I'm putting into the function, but the 2 only goes into the g. The g does whatever it does to it, and it spits out an output. That output is then what f links to, or f takes as its input. So f is this other formula, 7 squared plus 1, which we can see is also 50, right? Either one of those had better give us the same result. They are the same process. So if a question just asked me for the number, f of g of 2, I would do that the way I did the second problem. It's easier to just do it with the numbers. But if it asked me for the formula, then I'm looking for that first approach. And there's no reason you can't do f of f, or f of f of f, or any combination of 2 functions. You can find its composition. And it just means do the first function and then plug that into the second function. It does, the order does matter. So f of g of 2 here is not necessarily the same as g of f of 2. So the way I do the functions is going to give me a different answer typically each time. Are there questions about that composition that I just showed there? Okay. The question about solving for f of x, I'm not totally sure what that is referencing. If it's the take-home work for number 5, you're not actually solving, you're just graphing, right? So the sketching the graph, you're not solving the function. You're just trying to come up with a sketch and show that you're finding the sketch by sort of moving that original function around. Okay, there's a couple other questions here. May not be able to get to all of them, but let's take a look. So I'm just kind of looking through these questions to see which ones make sense here. Yeah, I mean, this question, so there's a question on this one. This is 2.2, number 21. It says match the data with one of the following functions. So it's giving you like the x and the y, and then you're supposed to pick which of these functions it is. So, you know, it's certainly possible that if you put in -3 here, you could get out -2 if it was the right constant. But it's not actually possible if I put in -3 to x squared, I can't get out a negative. Well, I could if it's the right constant, right? But these are the same c's. So the c that would work here for this value wouldn't work here for the value. And to me, the giveaway for this one is this point here, right? If I put in 0, it says it's undefined. Well, for both f and g and h, there's no problem with putting in 0 for x. So that tells me it has to be this function, right? R of x is c over x. So I know that. And then to make the function fit the data, I just have to pick one of these other values and put in x. Yeah, just put in like this one. If I put in x for 1, right, then that should equal 6. Terrible C, right? But then that's easy to see that C has to be 6. And you could, or wait, where am I? X is 1. Oh, I got it mixed up, that's why, right? C over X. Yeah, X is 1, and Y is that. So that has to be 6. You can check the other values and verify that that works. Okay.
I think I have a question about reflection and inverse.
Yes.
Because I understand, but sometimes it's difficult to make the inverse of the function.
Yeah, so good question. They are definitely different things.
Mm-hmm.
Let's see some. Let's talk about that briefly here. So an inverse function, so reflections are where we take a graph and we mirror it over, I mean, there are different ways of doing reflections, but the easiest reflections for us are mirroring it over the y-axis or the x-axis. And so that happens by, if I start with some function f of x, who knows what it looks like. If I put a negative in front of f of x, this is going to take all of the positive values and make them negative, and all the negative y values and make them positive. So this is going to be a, depending on your perspective, you could think of it in different ways, but I call it a vertical reflection because it's flipping things over. I know it's over the x-axis, but it's flipping them vertically. So this is a reflection over the x-axis. If, on the other hand, I make the x negative, that's going to flip things left and right. So that's going to be a reflection over the y-axis. Okay, so when we say reflections, those are flips of my graph over a particular axis. Now, an inverse function is doing something different. So sometimes students get confused because isn't sort of negative f of x the inverse of f of x, and it's not. You may be thinking of like 2 and -2 are inverses, but those are just numbers, right? We're looking at a function, a relationship. We want the inverse of the function. And it turns out that the characteristic of a function is that if f of x equals y, so if you have a function, there's a connection there, right, between inputs and outputs. The inverse of that is a function as well, and we call that function f inverse. We put this little -1 up there. And what it should do is it should undo what the function does, right? So if the function took x to y, then the inverse function should take y and turn it right back into x. It should undo what the function does. It's sort of the same way that like adding to and subtracting to are inverses, right? If you go forward 2 and then back 2, you end up where you started. You haven't changed things. The analogy in functions is that it should unravel kind of what the function does to the inputs. So this is really the key relationship here, that if you know what a function looks like, you know exactly what its inverse looks like, because they are defined as sort of complements of each other. So if the function has the ordered pairs, you know, if this is my function, well, then I know my inverse function. It's not equal to, right? But I know the inverse function because I just flip the x's and the y's. So if 1 goes to 2, then the inverse function has to take 2 back to 1, and vice versa. We can also see that when we look on a graph. So if our function looks like, that's a good example. If our function looks like this, what happens, it turns out, is that if you flip, like here's a point, this point looks maybe, I mean, I didn't put a scale on here, but maybe this point is 0, 1, let's say. Then the inverse function would have the point 1, 0. If this point here is like -1, 1/2, then the inverse function would have 1/2, -1. And as you flip those points around, you get a graph that looks like this. And so it turns out visually that if you take a function and you flip it over this diagonal line, so that is also, you could call that a reflection, but it's a reflection over this 45-degree line. What you get is the inverse, right? So if this is f, this is its inverse. If this is f, then this is its inverse. They're inverses of each other. So this is sort of a visual interpretation of what it means to flip the x's and the y's. And then sort of the final, you know, sometimes you might have a function that's given as a formula, and we might like to find its inverse from that. You could potentially graph it, I guess, and try and flip it and figure out what it looks like from that. To me, that seems like a lot of extra work. What we really want to do is just remember, if we flip the inputs and the outputs, then we should have the inverse function. So what we do here, this is the same function, but then if I flip the inputs and the outputs, I now have the inverse function. It's not quite right because it's like x equal, but if I just move things around a little bit, divide by 3, I get, and then I can just relabel that f inverse of x instead of y. It turns out that that is the inverse function. So I can solve for that algebraically as well. So those are like 3 different ways of coming up with the inverse function: flipping the x and the y, reflecting about the line y equal x, or sort of solving an equation to figure out what that inverse function is. And all of those require, we haven't mentioned this yet, but all of those require that the function is 1-to-1 when we start with. So, and you can see the problem, I think, if your function, so 1-to-1 means that each x has only a single y, that's a function, but also that each y has a single x. That's what makes it 1-to-1. Here, this is very clearly a function, but it's not 1-to-1, right? Because there's a certain y value that has 2 different x values. If you tried to flip that, it looks something like that. It's a little bit of an art problem, right? To figure out what the right flip is sometimes. And you can see the problem, right? This is no longer a function. So if you don't have a one-to-one function like this, see, this is fine. Each y value has only a single x value associated with it. So that function has a nice, well-defined inverse function. But if you start with something that's not one-to-one, it's still a function, but you can't have an inverse function. Okay, I don't know if that was your exact question, but it was something I wanted to talk about from inverses, and hopefully it covered that question.
Yes, but now I have other question about it. So those ones are inverse and reflection. What is the difference with transformation?
So transformations are like the reflections. So a transformation is where we're taking a graph and we're figuring out what it looks like by imagining it transformed, like moved around from some original graph. So reflections are a type of transformation.
Okay.
This idea here is similar in that we're sort of taking an original graph and moving it to get a new graph, but the meaning is a little different. We're really focused on the relationship between these. This is an original, and then this is its inverse. Whereas with these, the new function is just kind of a new function. It doesn't have this inverse property at all. So reflections are a type of transformation along with like a shift. So a shift was where you just, the graph starts here and you move it left or right or up or down or flip it. And so those are all types of transformations. You can also do some stretching. Right? You take a graph and you stretch it out one way or the other. So those are all transformations. Inverses are really a different idea. I mean, there's some similarities, but it's looking at something different.
So in the point 5, that we need to make a transformation, that means that the equation is going to be an absolute value of x plus 2 plus 1. Because I think I'm confused to make the transformation of the 5.
From the take-home work?
Yes.
Yeah, I mean, so I'll give you just a different example. Let's look at f of x equals,
With absolute value, please.
well, I don't want to, I mean, okay.
Please.
I mean, it doesn't matter. The whole point of transformations is it doesn't matter what your starting graph is. What matters is what's been done to it. So if you look at, it matters not what graph I started with. If I add x to the 3, this transformation is going to move the graph left 3 units. Whether it's an absolute value or a square root or some other function that we haven't even learned yet, it's going to move it left 3 units. This negative, because it's on the outside, that's this. It's going to be a reflection over the x-axis. So sometimes we call that a vertical flip. And then this plus 1, because that happened at the end, that's going to be up 1 unit. So these are the transformations that are made. And so that same thing, if I have negative x plus 3 squared plus 1, or negative the square root of x plus 3 plus 1, or negative absolute value of x plus 3 plus 1, those are all the same. I start with a different starting function, but then I move it in the same way no matter which of those functions I'm working with. Okay.
If I've moved to the left, it's because now it's negative.
The left 3 units,
Yes.
that's because it's x plus 3.
Okay.
So remember, the plus on the inside always moves it to the left. Each of these 3 things is totally separate from the others. So this movement here has nothing to do with any of the other parts. It's just from the plus 3, the x plus inside. Same here. That's negative on the outside, just does its thing independently of all the others.
Okay. I think I have one in the homework, but in the 12, I have one question there.
I'm sorry, which one?
In the 12,
Yeah.
I think it's section 2. Let me see. 2.5 transformations. 6B. I think I couldn't find the function.
Yeah, so you're starting with the graph of x cubed. And x cubed kind of looks like a here, but just shifted down and just starts right at the origin. So yeah, x cubed would look like kind of that function. So the question is, how can you take that base function x cubed and shift it and move it around till it looks like this function here? So I can see that it's been reflected or flipped, and there's actually a couple different ways of doing that. I might start, I guess the way I see it is that it was flipped horizontally. So it looked like this. And to do that, I put a negative inside the function. It turns out it's the same as if you flip it vertically, which would be a negative on the outside, and it turns out it doesn't matter. It's going to be equal to this. So either one of those are going to give you the same result. And then it's just a question of moving it. So I moved it, it looks like 3 units over to the left. I'm thinking of this point here. So that's going to be you have to be a little careful with this one. It's probably easiest to use this version here. But to move it to the left 3 units, I do an x minus 3. So it's going to move it over there and flip it, and then I have to move it, looks like 3 units down. So put a minus 3 there. Okay.
Okay, I think I was having the version. Oh no, what was no? Oh, I left the 3 positive, and that 3 is negative.
Yeah, so that's that left-right thing, right, that you asked earlier.
Okay. And other question I didn't memorize how the graphs are going. So in the exam, can I have like how the graphs are so I can see when it's flip over from the X whatever?
Well, you'll get a note sheet in the exam, so if you need to write that down, you can. There's only like 4 of them, right? I think the square root and absolute value, x squared. I'm sure I forgot one of them, right? But those are the main basic ones that we've covered in 2.6. So if you have trouble remembering those, you're certainly welcome to write those down on a note sheet. So there's also a question about the kind of vertical and horizontal stretching and shrinking. I will say it's not as critical. It comes up a couple times, but it's I guess we do more of it with quadratics, but other functions, the stretching and compressing kind of gets a little hard to be precise. Like you can know kind of roughly what it does, but it's hard to graph the things properly. If you multiply or divide, you're going to end up doing the stretching or the shrinking. And which direction you do it, horizontally or vertically, is going to depend on whether you did it on the, whether you multiply it or divide it on the inside by the x. Everything on the inside is going to be horizontal, and everything on the outside is going to be vertical. Okay. What happens also on the inside, it always does the kind of opposite of what you would expect, right? And that's what we're talking about, like the plus, when I add a 3 on the inside, that actually goes to the left 3 units, kind of counter what you might anticipate. And it's the same thing here. If I multiply by 2 on the inside, you might think that might double everything, but actually it shrinks everything by a factor of 2. So this is going to be a horizontal compression by a factor of 2. For example, f of x equals the square root of 2x. If my original square root function looks like this, my compressed version, maybe that was a bad graph to start with. Let me kind of stretch it out a little bit. So if this is the square root function, again, you can see it's like a little hard to draw, but this would be the square root of 2x. It takes all of those square root values and it kind of cuts them in half, shrinks them down by half. The vertical, it does kind of what you would expect to do. So if I multiply on the outside by 2, that's going to double all the y values. So that's going to be a stretch by 2. So for example, 2x squared. If this is x squared, 2x squared is going to double each of those values, and it's going to like stretch out my graph vertically. Okay, so those are the horizontal and vertical stretches and compressions. And again, if it's, you know, you may see one like that on the exam, or you may not. You'll certainly see some shifting and reflecting. Those are more important to me, and it's partly because when we shift and reflect, we can really almost know exactly what our new graph looks like. When we start stretching and compressing it, you know, you can see even from my graphs here, they're like kind of, they kind of lose their precision, right? They become pretty estimates, and it's not bad to have an estimate, but it's not as valuable as having the exact thing. Okay. Let me go back at a couple other questions from the homework. So let me take a look at those. Yeah, so here, number one here, use the graphs of f and g to graph this new function f plus g. So, f plus g, h of x is just, all it does when you add the functions together is it just adds the f value and the g value together. So h of 0 is going to be f of 0 plus g of 0. F of 0 is 2 and g of 0 is 0. So when you add those together, you just get 2. So your graph there is just going to start right at 2, right? And you just kind of move through as x goes to 1, right? I add that together and I get another value there. When x is 2, it's going to be 3 plus 1. So I get another value there. And then you can connect all of those with your line to get your new function h, right? So your new function is made up of just adding the f and the g together. And you do the same thing if it was multiplying or dividing or subtracting, right? You can create the new function just by point doing your operation with your kind of original functions, whatever they might be, f and g. Let me see, I think it was, no, that can't be right. Number 15. Yeah, so those are the compositions. There's another question. We can certainly look at this later, but these are just the compositions that we were talking about. So if you take f composed with g, I can do one of these here. This one, f composed with g, that's going to be f of g of x. And that's going to be f of x cubed plus 9. Writing here is poor, apologize. And then that value goes in here. So f of x cubed plus 9 is the cube root of x cubed plus 9 minus 9. And the plus 9 and the minus 9 cancel, and the cube root and the cube cancel, and you end up with just x. So that one ends up simplifying. That actually tells us that those are inverses. If you have two functions that when you compose them together give you x, that's saying, f does something and then g does something, and we end up right back at x where we started. So that doesn't ask you that, but that is what's happening with this one. Okay,
it wouldn't be the square root of x?
No, because it's a cube root, right? This is the cube root there.
Oh, okay.
So the cube root of x cubed, those are going to be inverses of each other.
Okay.
Yep. So yeah, they just end up canceling. Okay. Let's see. Let's do one or two more here, and then take a look at this one, and then I'm just gonna give a quick overview then of section 3 after this. I just forgot what they are. 3 and 8. Oh, well, there you go. I was seeing the future here, right? So this is just asking you to work through that they're inverse functions. So f of g of x right here, you're just going to put, this value is your g of x, so that goes right in here. And then f of g of x, this g of x value then will go right in here for x. And you're hoping that after you do your algebra and keep track of positives and negatives, and you should end up with X if they are inverses. And the same thing should happen if you go the other way around too. You technically do have to check both ways, that f of g equals x and also that g of f equals x, but you have to be pretty, you don't have to worry about that normally. If you just check one direction and you get x, you're going to be almost always safe. Okay. So that's how you can verify that two functions are inverses, by taking their composition, combining the two functions together. And then number 8. Yeah, so this is just inverses. So the inverse, you have x and f of x, and so the inverse function is going to flip those. The first point, it's not very interesting, right? Because they're both -2. So flipping them still gives you -2 and -2. But, you know, here, if I know f of -1 is 0, then I know f inverse of 0 is going to be -1. Right? And that's that important relationship with a function and its inverse, that you're really just flipping the inputs and the outputs. And that looks differently when you have ordered pairs or a graph or an equation, but it's really the same thing in all of those. An inverse is where you flip the inputs and the outputs.
I just have a quick question on that one.
Yeah.
I did that on the quiz and it marked all of them wrong for some reason.
Well, I'd have to look at your quiz. It could be, you know, that you flipped but sort of put them in the wrong boxes, or
Okay.
I don't know. So that is the right idea, but certainly send me a question about that and I can take a look at your individual quiz.
Okay.
Sometimes I can see like, oh, you just, you know, put a period in each time and so it marked you wrong, right? And I can give you credit for that. Sometimes it's something else. So, okay, so the last thing, I just wanted to take a minute here to preview section 3 for you guys. For those of you who are done with section 2, we'll just take 5 minutes or so here and preview what's coming up for us. So section 3 we're really focused on analyzing polynomials more carefully. It's not focusing. So we know a little bit about polynomials. We actually know quite a bit about certain kinds of polynomials. We know a lot about this, right? This is a line for us, but it's also a polynomial. It's a linear polynomial. It's degree 1, right? There's just a single x. We really know everything there is that's interesting about lines. So that one we know what they look like. We know what their intercepts are. We know how to describe a line. And we should also know about quadratic polynomials too. So we normally write quadratic polynomials like this, right? ax squared plus bx plus c. We can find, now you may be a little rusty on this. So 3.1 is kind of focused on going over and reviewing all of the details about these quadratic functions.
What's in the parentheses in the second one?
That's just an x,
Oh, okay.
some sort. I don't know. You're right. It does not look like an x. So it's just the difference here, of course, is that it has an x squared in the formula. So it's a quadratic instead of a linear. And we should recognize that that is a parabola. Which parabola it is exactly depends on the A, B, and the C. But once you learn how to find the vertex here and whether it opens up or down, and again, some of us already know that, we can kind of lock in on exactly which parabola this represents. And that's also one that a polynomial that we can kind of master. We can know everything that there is to know about that. But then the question is, you know, what about higher degree polynomials? What about f of x equals x to the 5th minus 4x squared plus 17x minus 2? What can we figure out about that, and what is important about that polynomial? And it turns out that as you get to these higher degree polynomials, we're not going to be able to master them like we will linear and quadratics. But we will be able to figure out some important features of these. And it turns out some very important features for us are called the end behavior. So like with this quadratic, the end behavior is kind of what's happening as the x's get really large and really small. And in this case, you know, both the ends are going up, right, to positive infinity, whereas this little graph, both the ends are going down. So the question is, can we figure out what's happening here on the ends? And it turns out you can. It turns out actually that just this leading term is the only thing that determines what your end behavior is. The other part we'd really like to know are the x-intercepts, right? So the x-intercepts are where the graph touches the x-axis, and those turn out to be really important points for us. We're not always able to find those, but we're going to learn some strategies and skills to help us find those. The y-intercept is also of value, but it's not always impact what our graph really looks like. And so once we have this kind of information, you know, maybe we know the end behavior looks like this. The other question is like, okay, I know the graph is going to hit this x-intercept, and what is it going to do there? Is it going to cross through? Is it going to just bounce down like a parabola? So those are some other questions that we are going to answer. Those involve something called multiplicities. That'll tell us what's happening with, you know, a function like this. And maybe by the end, we'll be able to get a rough graph that looks something like that. So we won't be able to know for sure what certain parts of the graph look like, but there are certain areas that we want to focus on. What's happening on the ends, what's happening right around each of these x-intercepts that are going to give us a very good sense of what the graph looks like. And then we're going to spend some time kind of thinking about the theory of polynomials. So how can we construct polynomials? What kind of x-intercepts different polynomials might have. And at that point, we'll have a very good understanding of polynomials. Again, it won't be perfect, but we'll have some tools to help us figure out what they look like. Okay. So when you get into chapter 3, you're going to start by focusing on the quadratic function, right? Really mastering how a quadratic function looks and works, and then we'll move into these kind of higher degree polynomials. In order to be successful with polynomials, we will have to spend a little time doing polynomial division. So that's, what is that, homework 3? And that is a little skill or operation that we need to help us figure out some of this information. Okay. And then we'll kind of put that all together in homework 4 to try and figure out these zeros or x-intercepts. Okay. So again, didn't really tell you how to do any of those things, but just a little bit of an overview so that you can kind of see what we're working towards in chapter or section 3. Okay. So that puts us, let's see, 250 here. So I'll go ahead and let you go, but certainly if you have a couple other questions, I know I didn't get to everyone's questions throughout there. If you want to stick around, I'm happy to spend a little more time and go over some of the other questions that you had. Otherwise, like I said, I'll try and send out a reminder email. Finish up your chapter 2 or your section 2 tonight, including the take-home work, and then please go ahead and get started on section 3 right away. I have the schedule posted. I will email that out as a little reminder, but you can get started on the homework. Give yourself time to kind of let these ideas sink in and master these ideas. Don't save it till right before the exam. That's going to make it really difficult. They're not the kinds of ideas that just come immediately. I mean, some might, but some might take you a little bit of time. So I want to encourage you, right, to get started early on that.